Here we are once again at the Microbac laboratory in Boulder. Here's our same compression tester, and we have to figure out how to put a wheel into this space here between the bottom and the crosshead at the top. The wheel is going to be supported by this fork, which is made of heavy-duty C-channel steel for any quick release wheel, in this case 100 millimeters, but Microbac also has a similar device for an axle length of 130 or 135 millimeters. Here is a second view. I'm going to take that picture there and make a graphic over here of the same device. So that's the basic device. There's the fork, and there's the wheel. Now, just to make sure that we understand the forces operating on the wheel in the compression tester, let's take this graphic here and turn it over, and then compare it to this picture here, which shows a rider coming toward me. And if I look at just the front wheel part here and superimpose that inside the compression tester, we see that all three of these are equivalent. The decrease in spoke tension that you'll see in our testing apparatus here as the crosshead moves down, ultimately causing the spokes at the top to go slack, is exactly the same as what happens over here when the spokes at the bottom of the wheel go through the load-bearing zone. These are three wheels we're going to compress to the point of destruction. Here is the extrusion and the mass of each of these three wheels. On the left is a Velocity Synergy rim. The middle is made of a Deep V, and the right is made of a Chucker rim. Other than the rim, all of these wheels are the same. They have the same hub, they have the same number of holes, they have the same spokes, they have the same nipples, and they all are tensioned to the same tension. Next, you're going to see, one at a time, each of these wheels put under compression until the wheels fail. And then we'll collect some data and do a little analysis. In the first case, you'll see the rim collapse quite far. And the next two, once we already know that that's going to happen with continuous compression, we stop the test a little bit earlier. You may also notice that the force being applied to the wheel from the crosshead moving down increases at differing rates, and I'll explain that to you also in a few minutes.
It started at 700 pounds. Is that wooden, right? Jeez.
You really got 1,000 pounds on it? The spokes at the top have gone slack. We got almost 3/4 of a ton. So the plate is still coming down, but the force is decreasing.
Yeah, there's no structure to it anymore.
Right.
So it's just bending it.
This one, I think, in terms of the mass, is in between those two, so we should probably see it collapse in between also.
Making a lot more noise.
Top two spokes are now slack, but only those so far. Yeah, we were well over 2,000 pounds with the other one at this point.
There it goes. It's down now. Of course, they're all going.
It's making a lot of noise. Yeah, we just keep on letting the plate come down. Nothing significant is going to happen. It's just going to bend more and more, but nothing else.
Yeah.
What does it tell you that it doesn't fail explosively?
The metal's ductile.
Yeah.
Oop, hang on a minute.
Whoops.
Stop it. I want
Wrong direction again.
slide yeah, that'll be alright. Let's come to the contact though.
Yeah, it's gonna be. Okay, you got enough friction so it won't turn. Okay, that's a good starting point.
Yep.
Holy mackerel. We're already over a ton. Folks are at the top are starting to fall. So they've lost their tension now.
That's failed.
Yeah.
Push everything down.
Yep, so that's, I think that concludes that one. Here is data for the velocity chucker rim, as we see here, and we see in the left column the amount of the crosshead moves down, and in the middle column the load in pounds, and in the right-hand column time in seconds. We continue at the bottom there. That whole first column is really when the machine is really getting prepared to start into some serious compression, which really we can start to register in the second column here with 200 pounds here, about 500 here, about 1,000 here, about 1,500 here, and about 2,000 pounds here. And then continuing into the third column, at this point here we have our maximum weight or load of 2319 pounds, and over here the numbers actually start to decline as the rim is losing its structure. Let's look at part of that again in case I went through it a little bit too fast for you. At 200 pounds here we're at 5.8 seconds. At about 8 seconds we're at 500 pounds. And at about 11.5 seconds, we're at 1,000 pounds. At 19 seconds, 1,500 pounds. And at about 36 seconds, we're about at a ton, about 2,000 pounds. And then we creep up to the maximum force of 2,319 pounds at about 75 seconds. Here is a chart that shows all three graphs on the same graph together. Down here is the maximum peak load after which the rim is not able to support the increasing weight being put on it by the crosshead. This line here is the velocity synergy. This is the deep V, and this is the chucker. And if you look to the left, you see the 2319, which was the number of pounds, the maximum weight that was supportable by the wheel that had the velocity chucker as its rim. Let's go a little further with this and take a look at these extrusions here and the circles representing the color above in the graph. So here we have an extrusion of the chucker with a blue rim. Here is the extrusion of the velocity deep V, and here is the extrusion of the velocity synergy. These all have the same circumference, but they have different masses. The mass of the chucker is 640 grams, the deep V 580, the synergy 520. They all have the same density of 2.8 grams per cubic centimeter. So that enables me to calculate the volume of aluminum alloy in the rim. So we have, in the first case, 229 cubic centimeters, then 207 cubic centimeters, and 186 cubic centimeters. From this information, I can calculate the area of aluminum in the cross section. Here it is in square centimeters and here in square millimeters. So for the chucker, I have 117 square millimeters of area of aluminum in the cross section, with the Deep V 106 and with the Synergy 95. So it certainly appears that there is a relationship between the strength of the wheel containing these three rims that relates directly to the amount of material in the cross section. Here's what we need to understand about this compression tester. It has a capacity of 34 tons, and this cross plate for this experiment is programmed to descend at a rate of 1/2 inch per minute. And it's going to descend at that rate whether there's nothing under it, or whether there's a guitar, or a bicycle wheel, or a concrete block. The compression tester will develop enough force to descend at that rate of 1/2 inch per minute no matter what. And that means that for the crosshead to move down the same distance per unit time, a stronger wheel requires a larger vertical force. It's interesting to note what happened to the hubs in these three wheels. All three of them ended up with an axle that was still straight, but there was some damage to the bearings, particularly the wheel on the right, which sustained the largest downward force. There was quite a bit of roughness in the bearings that we detected when we spun the wheel after the experiment. Now, this is the same graph, even though I've changed the appearance of it a little bit. And this is the origin here. This is where we have no extension of the crosshead. This would be 0.1 inches, 0.2 inches, 0.5 inches, and 1 inch, and under that is the time it takes to achieve those amounts of extension. There's actually quite a bit of interest that happens in the early stages of this graph, so let's expand this part here. Here's the expanded graph. Let's fit some straight lines to these curves. First for the Deep V, and then the Synergy, and then the chucker. We can make a few observations about where the straight lines diverge from the curved ones, and we see that for the chucker and the Synergy, the lines diverge at about 400 pounds, so the line is linear up to about 400 pounds. With the Deep V, the line is linear up to about 600 pounds. The rim should be considered to have failed as soon as we get a substantial flat spot in the rim, and you can certainly see that developing rather quickly in the compression testing clips that you've seen. And this is going to be at the point in time where the curved line starts to diverge from the dashed straight lines that you see in the graph below. This is interesting because if we just compare the velocity Deep V on the left with the chucker on the right, we find that a wheel made with the Deep V is going to be stiffer in a radial direction than the chucker. And that is true even though we saw on the earlier slide that the chucker does not completely cave in until a larger force is put on it than is the case with the Deep V. Still, 400 pounds that a wheel can support made with a Velocity, Synergy, or chucker is still a very, very strong wheel, and that's a lot of weight, but the Deep V can support even more. This apparent conflict of information I think we can resolve in the top graph when we look at the Velocity chucker. It is able to support the largest load before it totally collapses, but it does that at the expense of its performance as an elastic member of the wheel. Whereas in the case of the graph below, we see that the Velocity Deep V cannot support quite as much weight before it collapses, but can support more weight while remaining within its elastic region, which is what the wheel requires.